So one more example here. The only reason I put this example last, which implies that it's the hardest one, is because here the relationship between the variables that we need in this problem happens to be trigonometric. So we're going to model this situation with an equation we know from trigonometry. The math is the same kind of thing, so same kind of process. I have a hot air balloon that's going to leave the ground and go straight up. And I have somebody over here on the ground. This is an eye. Somebody over here is watching. So as the balloon gets higher, the angle of this person's eye, or the telescope, or whatever it is that's watching the balloon, this angle is increasing. I'm going to call that angle theta. And I know the distance, the horizontal distance between where the balloon lifted off and where the watcher is watching is exactly 500 feet. So what do I know about this problem? I know that at the exact moment when theta equals pi over 4, that the rate at which the angle is changing is at 0.14 radians per minute. I know that distance between the liftoff point and the eye is 500 feet. I know the balloon's going straight up. So h is increasing. Do I know how fast h is increasing? No, that's what I'm supposed to find. Okay, so find how fast is the balloon rising if I know these other things. So the thing I'm interested to know, the thing I seek is, we seek dh dt. And I know something about d theta dt. I know a little something about theta. So the two rates that I know, the two rates that are related, are the rate at which theta changes and the rate at which the height of the balloon changes. So I need an equation that relates this angle to this height. So I also happen to know the length of this, and that distance there is not changing. So the equation we can write here is that the tangent of an angle, so in this case the tangent of theta, is the, okay, SOHCAHTOA, right? So opposite over the adjacent. So the opposite, the side of the triangle opposite the angle is h. And the adjacent side of the triangle is always 500. We could give it a letter name, but we know it's always 500. It doesn't happen to be changing. So this is the equation I'm going to use. This does relate theta and the height. So my next step, I'm going to take the derivative of both sides of this equation with respect to time. The derivative of tangent is secant squared, with the inside the same, times d theta dt equals, now h over 500, that's just the same as 1/500th of h. So you could use the quotient rule, you don't have to use the quotient rule. So it's just 1 over 500 times, what's the derivative of h? The derivative of h with respect to h is 1, and then the derivative of h with respect to time is dh dt. So what's left to do? I'm going to plug in the things I know, the values I know, and I'm going to try to isolate the thing I wanted, which was dh dt. So I know d theta dt is 0.14 radians per minute, so 0.14 equals 1/500th dh dt. The only thing left to do is figure out the secant of theta and to square it. Well, I know that the moment I'm talking about, theta is pi over 4. So it's going to be secant squared of pi over 4. Secant is the reciprocal of the cosine. Well, cosine of pi over 4 is, you probably remember it as radical 2 over 2. It's also the same as 1 over radical 2. So what's the reciprocal of 1 over radical 2? It's just radical 2. So I'm going to take radical 2 and square it. So that's going to be 2 times 0.14 equals 1/500th times dh dt. I'm going to isolate dh dt. So you sort of have two options here. You can keep your units with your values all the way through this problem to get the units at the end, or you know the thing you're isolating, whoops, was dh dt. There we go. So what are the units on dh dt going to be? Well, the units on height in this case are feet. And the units on time in this problem are minutes, so it's feet per minute. So 140 feet per minute.